Good morning, everyone. Good morning, everyone. So, uh, shall we begin the session? I said, shall we start the session? I'm asking from you. If everyone is available, then we can start. All right. Wait for another 5 minutes. Now, shall we start? All right. So in the last class, we have started about the how to create the image, that is how to view the image, or we can say how to create the image or image formation in the eye. So if I'm talking about the ordinary or the simple camera, the lens has a fixed focal length and the focusing at the various distances that is achieved by the various distance or by varying the distance. That means there is a gap between the lens and there is a gap between or distance between the lens and the imaging plane where the film is located. And in the case of the human eye, the converse is true. That means if there is a change in the distance, that is the fixed length that is different from the camera. So if I'm talking about the human eye that is different from the camera focusing length, that the lens has a fixed focal length and focusing at the various distances that is achieved by varying the distance between the lens and the imaging plane. But in case of the human, yes, that is totally opposite of this one. The distance between the lens and the image region is fixed in that case, and the focal length is needed to achieve the proper focus that is obtained by varying the shape of the lens. It depends on the purpose to purpose that is used. If I'm talking about a eye, that is human eye, this is one of the example, this is one of the diagram that is given, how it will be focused or how it will be viewed, that we can say the tree that is with the looking at a palm tree. Point C is the optical center of the lens. So this is a graphical representation of the eye looking at a palm tree that is used for the distant or near objects respectively, and the distance between the center of the lens and the retina along with the usual axis is approximately 17 mm, and this is, we can say, approximately, and there is a focal length that ranges from the 14 mm to the 17 mm. That range for that the distance is greater than the about 3 m. Geometry, if I'm talking about the geometry in the 2.3, that illustrate how to obtain the dimensions of the image formed on the retina. For example, if I'm talking about a person that is viewing the tree from the C point, that is used to obtain the dimensions of the image that is found on the retina. And if I denote the height with the edge of that object, the geometry will be 15 upon 100, and 15 divided by 100, that is equals to the h divided by 17, or h equals to 2.55. Next one is brightness, adaptation, and the discrimination. Now, this is, we have already studied in the last class, that is what is the difference between the brightness, adaptation, and the discrimination. Now, first of all, my question is why these three terms are required? What is the usage of these three terms? Yes, very correct. Brightness means increasing the size, increasing the quality. Then adaptation means that is the range that from the visual system is adapted in the enormous, that is an order of the 10 power 10, that is used in the experimental evidence that indicates subjective brightness. This is for the BA, then this is the BB, this is the scotopic and the photopic. This is the log of the intensity, that is ML, and the subjective brightness. The subjective brightness is a clear limit, and this is the scotopic threshold. And this is the range of the subjective brightness sensations showing a particular adaptation level. So this shows a particular adaptation level that is ranged with the subjective meters. An essential point in interpreting the impressive dynamic range that is depicted with such operations which cannot operate over such a range simultaneously. Rather, it is also used or accomplish this large variation by changing the overall sensitivity. That phenomenon is known as a brightness adaptation. And for any set of condition, the current sensitivity level that is increased, that is done, or level of the adaptation that is rather than the small that we are using. So that term is known as a brightness adaptation, that changes with the overall sensitivity, or that change with the overall phenomenon, we can say that phenomenon is known as a brightness adaptation. And when we talk about the total range of the distinct level that the eye can discriminate, eye can use simultaneously is rather than small when compared with the total adaptation range. So when we compare with the total adaptation range that is used with the brightness, that is used with the visual system, that is used with the brightness adaptation level, and that ranges with the delta I, that is a change, that is the ability for the eye to discriminate between the change, to discriminate between the levels, between the changes in the light intensity at any specific adaptation level is also of the considerable interest, that is for the BA and the BB. And there's a classical experiment used to determine the capability of the human visual system for bright discrimination that consists of having a subject look at a flat illuminous area that is used to occupy the entire field of the view. That is represented by the illumination, that is the increment of illumination, that is the delta I, that is a short duration flash that appears as a color in the center of the uniformly illuminated. Now, there are two terms if the delta I is not bright enough or if the delta I gets stronger. There are two terms that is used in this one. If that is not bright enough, that the subject says no, that indicate no perceivable change. When the delta I gets stronger, the subject may give a positive response of yes, that indicated a perceived change. So there are two terms, not bright enough, gets stronger. And there's a delta IC, that is the increment of the illumination discrimination that 50% of the time with the background illumination, that is known as the Weber ratio. There is a Weber ratio concept that is used with the delta I and the I. Now, let's move to the next phenomenon that we have studied, that is this is done. Any doubt in this diagram? How it formed? That is what is the diagram of the Weber ratio that represents the function intensity? And that has a general shape that is shown in figure 2.6, and this curve shows that the brightness discrimination is poor when it is taking the Weber ratio is large at a low level of the illumination, and also improve the, we can say, the background illumination increases. And if the background is held constant and the intensity of the other source is used instead of the flashing, that is also not allowed from never being perceived, that is never perceived means never being achieved for that target. Next phenomenon, that is a two phenomenon that is used that clearly demonstrate that the perceived brightness is not a simple function of intensity, rather it is an overall intensity discrimination. The first fact is that the visual system tends to undershoot or overshoot around the boundary of the regions. The second phenomenon, that phenomenon is known as the match bands. Second one is a simultaneous contrast. That means the same brightness will be applicable for two up to three images. That is used its intensity as a brightness. This is one of the example. There is the actual intensity, there is the perceived intensity. Actual is represented with the squares, perceived intensity over here. This is the illustration of the match band effect, that is perceived intensity is not a simple function of the actual intensity. However, they appear to the eye to become the darker as the background gets lighter. And a familiar example is a piece of the paper that seems white when lying on the desk but can appear totally black when used to shield the eyes when looking directly at a bright sky. So when we are looking directly on a black sky or the bright sky, that is to look directly to shield the eye. And the other examples of the human perception phenomena are the optical illusions in which the eye fills in the non-existing information or wrongly perceive the geometrical properties of the objects. The same effect, this time with a circle, can also be seen with a few lines that are sufficient to give the illusion in various terms. These are the various examples that show the simultaneous contrast. All the inner circle have the same intensity, but they appear darker when the background colors become lighter. This is a simultaneous. Simultaneous, same time. The background color as well as the foreground color will be changed. You see the difference. In the first part, the background color is more darker. Second part, lighter than the first one. Third part, more lighter than the first part. But when you talk about the foreground color, that is the center color in a square, that have a first one has a darker color. Sorry, first one has a lighter color, then more darker, then in the next one is more darker than the two images. This is one of the example of the simultaneous contrast. contrast. In the same way, there is the optical illusion that is also carried out with the square. Now this is a square, or sorry, this is a circle. This figure where my cursor is moving, this is a circle that is represented with the various lines, that is the optical illusion. In the same way, in the first figure, there is a square that also formed with a circle, dark circles. Then these are the arrows, these are the squares, and the two horizontal lines are of the same length but appear shorter than the other. Finally, there is an orientation at the 45 degree that are the equidistant and the parallel, and there is a cross-hatching creates the illusion that those lines are far from being parallel. And there is an optical illusion that are a characteristics of the human visual system that is not fully understood. So that is not fully understood with the visual system of the optical illusions. Now, next one is electromagnetic spectrum, that is denoted by this. This is the alpha equals to C, or wavelength equals to C upon or divided by V. That means, yes, this is the wavelength and frequency that is represented by the V. And this is the energy of the one photon, that is the electron volts. This ranges from the 1 to the 10 power 6 and the 1 from the to the 10 power 9. Then in the next one, that is the frequency hertz, that ranges from the 10 power 5 to the 10 power 21. Then wavelength, that also range from the 1 to the 10 power minus 12, then 1 to the 10 power 3. So these are the various wavelength, energy of the one photon, then wavelength in meters. In the same way, there are the gamma rays, X-rays, ultraviolet, infrared, microwaves, radio waves, and there is the visible spectrum. So this is the figure that shows the electromagnetic spectrum. There is a visible spectrum, so there are visible equation that is shown zoomed to facilitate the explanation, but there are visible spectrum that is rather narrow portion of the EM spectrum. Where C is the speed of the light, the energy of the various components of the electromagnetic is given by the expression. This is the E equals to HV. And this is the example of the electromagnetic waves. And that bundle of energy is also known as a photon, where the energy is divided into the various proportions, that is known as a frequency. So high frequency, yes, with the increase with the high frequency, that will be changed, that will be taken out with the radio wave that have a photon with the low energies, and microwaves have the more energy than the radio waves, infrared still more, than visible ultraviolet X-rays, and finally the gamma rays, that is the more energetic at. And when we talk about the light, that is a particular type of electromagnetic radiation that is sensed by the human eye. And the color spectrum is also expanded in figure 2.10 for the purpose of the discussion that is explained over here. And there are multiple types of the spectrum. One is known as a monochromatic, that is achromatic light, that is attributed is the intensity or the amount. Then chromatic, that spans the electromagnetic energy from this is the range. Then there's the medical and the astronomical imaging that is used for the image radiations in the nuclear environments. Then chest and the dental X-rays are in the low energy, that is soft end of the X-ray band. And the part of the infrared band close to the visible spectrum is known as the near infrared region, and the opposite end of this band is known as the far infrared region. So there are two parts. One is a near infrared region, one is a far infrared region. And this latter region blends with the microwave band, and this band is also well known as a source of energy in the microwave ovens. When we use the ovens, that how it will make the things as a hotter and hotter and hotter. There is a far infrared region that is known as a source of energy in the microwave oven that has many uses, including communication and the radar. And finally, the radio wave band encompasses television as well as AM and the FM radio. And in the higher energies, radio signals emitting from certain stellar bodies that are useful in the astronomical observations. And in most of the principle, it ranges from the 10 power minus 10 M. And the other major source of the digital images are electronic beam for the electron microscopy and the synthetic images that is used in the graphics and the visualization. Next one is the image sensing and the acquisition. So most of the images in which we are interested are generated by the combination of the illumination source and the reflection or the absorption of the energy from that source by the elements of the scene that is being captured or that is being imaged. So that is the image sensing and the acquisition that is used with the illumination source and the reflection or the absorption of the energy from that source. And we use two words, that is the illumination and the scene, in order to emphasize the fact that they are considered more general than the familiar in which a visible light source illuminates. So when the visible lights illuminate a common 3D scene, that is known as a three-dimensional scene. For example, the illumination may originate from a source of electromagnetic energy such as the radar, infrared or the X-ray system. That illumination will be used as a source of the electromagnetic energy. But as noted earlier, it could originate from the less traditional sources such as electrosound or even a computer-generated illumination pattern. An example in the first category is a light reflected from a planar surface, and the example in the second category was when the X-ray passed to a patient body for the purpose of generating a diagnostic X-ray film. That is one of the example when the X-ray is passed, when the X-ray is going. Yeah, when the X-ray is going for a patient body for the purpose of generating a diagnostic X-ray film. And in some applications, the reflected or the transmitted energy is focused onto the photo converter. There is the photo converter, that is the photosphere sensor or screen that converts, which converts the energy into the photo converter that is used. And in some applications, the reflected or the transmitted energy is focused on the photoconverter that converts energy into the visible light. And there's the electron microscopy and the other some applications of the gamma imaging also use this approach. For the mechanisms. And this is the figure that shows a three principal sensor arrangement that is used to transform illumination energy into the digital images. And this idea or the idea is very simple, that is the imaging or the incoming energy is transformed into the voltage by the combination of the input electrical power and the sensor material that is responsive to the particular type of energy being detected. So whatever the energy, whatever the type of the energy that has been detected, that is used for the combination of the input electrical power and a sensor material that is responsive to the particular type of energy that is being detected. Then next one is a voltage, the output voltage from where the output will be going. Output voltage waveform is in the response of the sensors, and the digital quantity is obtained from each sensor by digitizing the response. So by digitizing the response, it is used for the response of the sensors. And this is used for the image sensing and the generation that is discussed over here. Now, this is a figure that shows first part is a single imaging sensor. There is a filter, energy, power in, housing, voltage waveform out, then sensing materials. So these are the various forms of energy that has been converted, that has been transformed. That is a single imaging sensor. The next one is a line sensor. Line sensor means everything in the sequence. Then next one is the array sensor. So single imaging sensor, then line sensor, then array sensor. and one image line out per increment of the rotation and the full linear displacement of sensor from the left to the right. So one is available with the left to the right, that is combined a single sensor with the motion to generate 2D image. There is a 2D image that is also generated with the sensor that is combined with a single sensor that is with the motion to generate a 2D image that is being created. This is used for combining a single sensor with the motion to generate a 2D image. There is a sensor film rotation and one image line out per increment of the rotation and the full linear displacement of sensor from the left to the right. Just do one thing, read out this one because this is a fact and this is used in the next part, that is using the single sensors using double sensors. So just do one thing, read out this one, and if there is any doubt then please clear the doubts. Now let's talk about the image acquisition that is using a single sensor. Only one sensor is available for the imaging, like a thin film transistors that is available, or simple when we talk about the cameras, there is only a single sensor that is available, that known as a film. And the old cameras we say that the film is not working, and if I'm talking about the TV, television, in the previous days we say that the tube is not working or the tube is not not good, or tube is shocked out, then the TV is not working. So there is a single tube, there is a single sensor that is available over here. And there's a film, this is a film, that is a film roll, this is the rotation that carries multiple rolls on the one strip, that is known as a film, then sensor. And this is the linear motion over here. And one image line out per increment of rotation and full linear displacement of sensor from left to the right. So this is the image line out per increment of the rotation that is used with the full linear displacement that is used with the sensor from left to the right. This is combining a single sensor with the motion to generate a 2D image. The next one is the image acquisition using a single sensor. So figure 2.12a shows the component of a single sensors, and the most familiar sensor of this type is photodiode, which is constructed of silicon material and whose output voltage waveform is proportional to the light. That is also proportional to the light, that is also familiar with the light, that is a voltage or the output voltage. The use of the filter is in front of a sensor improved selectivity. There is a selectivity in case of the filter that is in the front of a sensor. For example, when there is a green filter in the front of a light sensor favors light in the green band of the color specific spectrum. So there is color specific spectrum. Yes, only one image will be line out per increment of the rotation and the full linear displacement of the sensor from the left to the right. Only the single line or the single image. For example, when we talk about the grass or the green filter in front of the light sensor that favors light into the green band of the color specific or spectrum, and as a consequence or as a data, the sensor output will be stronger for green light rather than for the components in the visible spectrum. And in order to generate a 2D image using a single sensor, there has to be a relative displacement in both the X and the Y directions between the sensors and the area to be imaged. The next figure is figure 2.13 that also shows arrangement that is used in the high precision scanning where a film negative is mounted on a drum. This is one of the example. And this is the one of the example where the film is mounted on a drum. When this says that mounted means rotated on a drum. Whose mechanical rotation provides a displacement in one dimension. So whose mechanical rotation, whatever the mechanical rotation, that provides a displacement in one dimension. And there is a single sensor that is mounted on a lead screw that provides a motion in the perpendicular direction. So the perpendicular direction that is used in the motion. And because the mechanical motion can be controlled with high precision, with the high values, this method is inexpensive. I agree this is an expensive method, but slow way. This is an expensive method and also the slow way to obtain the high resolution images. And other similar mechanics or mechanical arrangement that also uses a flat bed with the sensors moving into two linear directions. These type of mechanical digitizer sometimes also refers to the micro densitometer. So that sometimes refers to the micro densitometer that is used with the mechanical digitizers. Another example of imaging with a single sensor places a laser source coincidence with the sensor. There's a laser source that is used with the coincidence with the sensors, and that also used with the moving mirror that are used to control the outgoing beam in a scanning pattern and to direct the reflected laser signal on the sensor. There's a reflected signals or reflected laser signal that is also available on the sensor, and this arrangement can be used to acquire imaging using the strip. So that imaging will be used to acquire over the strip and array sensors, which are discussed in the following two sections. So one is a single strip, single sensor. One is the sensor strips, that are multiple strips that is mounted on a drum. So geometry that is used much more frequently than single sensor that consists of an inline arrangement of the sensor in the form of the sensor strip. So there's a sensor strip. This is available with this sensor strip. First one is the image A that is used with the image acquisition with the linear sensor strip, then with the circular sensor strip. This is the linear, this is the sensor strips. So there are two terms. One is the linear, that means in a sequence. One is the circular sensor strip. So this is a diagram that shows the linear motion. So one image line out per increment of the linear motion. That means one increment or the one image line will be available. This is the one image line that will be available that is used for per increment of the linear motion. This is the linear motion. This is a sensor strip, then imaged area. So this is one image line out per increment of linear motion. Then this one is the image reconstruction. And this is a cross-sectional images of 3D object. This is the cross-sectional images that is used with the various strips. Then this is a 3D object, linear motion, sensor ring, X-ray source. This is a 3D object that is used. Then this is the linear motion. Then there is a sensor ring that is also available, and there is a X-ray source. And when we talk about the sensors or using a sensor strip, that consists of an inline arrangement of the sensors in the form of the sensor strip. And this strip provides the imaging elements in one direction, and the motion perpendicular to the strip provides imaging in the other direction. So this strip also provides the imaging in one direction, and the motion perpendicular provides the imaging in the other directions. And this is the type of arrangement used in both or most flatbed scanners. And sensing devices with 4000 or more inline sensors are also possible with the sensing device. And when we talk about the inline sensor that are most used routinely in the airborne imaging applications, in which the imaging system is mounted on an aircraft. Mounted on an aircraft means that is rotating on an aircraft that provides or that files at a constant altitude and speed over the graphical image that is to be imaged. And there's a one-dimensional imaging sensor strip that also responds to the various bands of the electromagnetic spectrum that is mounted perpendicular to the direction of the flight. And the lenses or other focusing schemes are also used to project the area to be scanned onto the sensors. And when we talk about the sensor strip that is mounted in a ring configuration, ring method that are used in a medical and industrial imaging to obtain the cross-sectional images of the 3D objects. And the rotating X-ray source provides the illumination, and the sensor opposite the source that collects the X-ray energy that passes through the object. And this is the basis for the medical and the industrial computerized axial tomography, that is a CAT imaging. And it is also important to note that the output of the sensors must be processed by reconstruction algorithm, whose objective is to transform that sensed data into the meaningful cross-sectional images. In other words, images not obtained directly from the sensors by the motion alone, they require the extensive processing. And there is a 3D image or digital volume consisting of the stacked images that is generated as an object is moved in a direction that is available with the CAT or the MRII and the PET, that is a magnetic resourcing or resource imaging, and the position emission or emission tomographic. Last one is how to use the image acquisition using the sensor array. That is how to use the array combination of the various steps. So this is we can say we use an individual sensor that is arranged in the form of the 2D array, and there's a numerous electromagnetic and some electrosonic sensing devices also frequently are arranged in an array format. And this is also the predominant arrangement found in the digital cameras. And there's a typical sensors that is also used for these cameras is the CCD cameras, which can be manufactured with the broad range of the sensing properties and can be purchased in an array of the 4000 into 4000 elements or more. Then CCD sensors are also widely used in the digital cameras and other lighting sensing instruments. Whatever the response, that is the response of each sensor is proportional to the integral of the light emitting or light energy projected onto the surface of the sensors. That property is used in the astronomical and other application that requires a low noise image. And the noise reduction is also achieved by letting the sensor integrate the input light source or signal over the minute or even the hours. And because the sensor array is a two-dimensional, its key advantage is that a complete image can be obtained by focusing the energy pattern on a specific on the surface of the array. That is used with the surface of the array, that is used with the imaging of the array. Now, what is the main principle or the principal manner in which the array sensors are used? That is explained in the figure 2.15. Okay, so just read out all these things. So the next part is the image acquisition using the sensor arrays. We are using the sensor arrays for this concept. We are using what are the various sensor arrays. This shows the individual sensors arranged in the form of the 2D array, and the numerous electromagnetic and some electrosonic sensing devices also frequently are arranged in an array format. That is also known as this is known as a predominant arrangement that is found in the digital cameras also, DigiCam that we say, and there's a resolution that ranges from the 4000 into 4000 elements or more. Then CCD sensors are more widely used in the digital cameras and other light sensing instruments. And the response of each sensor is proportional to the integral of the light energy projected onto the surface of a sensor. That is a property that is used in the astronomical and other application that requires a low noise images. And when I talk about the noise reduction, that is achieved by letting the sensor integrate the input light signal over the minutes or even the hours. And because the sensor arrays is a two-dimensional, its key advantage is that a couple or complete image can be obtained by focusing the energy pattern onto the surface of the array. That means the main focus is on the surface of the array, the main focus is on the bulk of the energies. And the motion obviously is not necessary, as in the case of with the sensor arrangement that is discussed in the preceding two sections. And whatever the principal manner, whatever the area that is used in which the array sensors are used. And this figure shows the energy from the illumination source being reflected from a scene elements that is mentioned in the beginning of this section, and the energy could be transmitted through the sense or scene elements. The first function that is performed by the imaging is to collect the incoming energy and focus on the image plane. This is a figure that shows the digital image acquisition process. There is energy, that is energy illumination source, and element of a source, that is a scene source. Then imaging system, this is the imaging system. Then projector of the scene or projection of the scene onto the image plane. This is the projection, how the image will be projected. Then the digitized image. Digitized image means an image that is used for the digitizations. And the finite that is used with the image creation, that is used with the image method. And the function fxi may be characterized by the two components. There are two components of this one. First one is the amount of the source illumination incidence on the scene being viewed. Whatever the element that is destroyed, whatever the scene that is destroyed over here, that is viewed over the elements. Then amount of the illumination reflected by the objects in the scene. Whatever the amount of the illumination that is objected in the scene, then these are known as the illumination and the reflections component that are denoted by the IXI and the RXI. And the two functions that is used as the product to form fxy is IXI into the RXI. And the sensor array, which is coincidence with the focal plane, produces output proportional to the integral part that produces the output to the, that is, we can say proportional, that is integrated with the integral part of the light that is received at each signal, and the digital and analog circuitry sweep these output and convert them into the analog signals. That converts them into the analog signals, which is then digitized by the other scenarios, other sections of the imaging system. Now, what's the output? Output is a digital image that is produced with the digital cameras. This is one of the example. This is an example that is given of the digitized image. This is a digitized image. That is the output. This is the input, and this is the processing. This is the output. And as a consequence, that must be non-zeros. That must be zeros, and the finite, and that is the fxy that ranges from the 0 to the infinity. And the function may be characterized by the two components, that is the amount of the source illumination that can be viewed and the amount of the illumination that is reflected by the objects in the scene. And appropriately, when we say these are known as the illumination and reflections components that is used. And this is also the image formation that is expressed, that IXY is ranging from the 0 to the infinity and the RXY is ranging from the 0 to the 1. Ranging means the minimum value is a 0 and the maximum value is infinity in case of the IXY, and the minimum value is 0 and the maximum value is 1 in the case of RXY. And this also indicates that the reflections or the reflectance is bounded by the 0 and the 1. And the nature of IXY is determined by the illumination source that is determined by the characteristics of the imaged object. And the areas of the following average numerical also figure that illustrate some typical range of the IXY for the visible light. There's a L equals to F x0 y0 that is ranging from the minimum to the maximum. Now, the next topic is the image sampling and the quantization. That means what are the various image sampling methods and what are the various quantization methods that we are going to discuss in the next class, that is in the tomorrow's class, Friday's class. So that's all for today's session. If there is any doubts, any query regarding the assignment, regarding the module, any